Hello everyone. Today I will going to deliver a lecture on earthquake resistance design parameter and reinforcement concrete. Parameter of reinforcement concrete. First of all, I will discuss of failure modes of RC structure during the earthquake, which is include transverse versus compressive reinforcement, and then shear versus flexural failure, then weak beam, strong column, then soft story and column effect. And second part will be column or code prescribed seismic detailing RC structural element, and it will be included seismic detailing of material, major seismic detailing of flexure, which is beam, and whose member is axial force is less than F prime C divided by 10, and major seismic detailing of axial force member, and major seismic detailing of joint frame, and seismic detailing of flexural member, which is more moderate seismic risk zone, and moderate and seismic detailing of axial member, which is moderate axial risk zone, and ductility design shear wall, and seismic design and detailing of RC frame, or we can say the earthquake resistance design of beam and column. And then earthquake resistance design of flat slab or conceal beam, and we will not discuss today. And another topics in earthquake resistance design of steel structure, so we will not discuss here. So let's see this portion. Let's start. Okay. Earthquake resistance design parameter. We can see the transverse parameter. At first I will show transverse versus compressive reinforcement. We can see tight column and spiral column. Spiral column gives the lots of more strain compared to the tight column, and that's why we'll use the spiral column. We have been used the law of 5 factorials. We have used more than tight column, as we have been used 0.70. Okay. You can see the shear failure, which is occurred suddenly, and the shear failure is occurred to 45-degree angle. Okay, you can see here another failure mode of earthquake terrain, earthquake within shear failure of concrete partial. The slide is taken from Dr. Anam sir. I must respect him. Here the transverse versus compressive reinforcement, the ductility and ultimate deformation capacity of reinforcement member largely depend on the elevation depend on the level of the confinement of the concrete, as shown 3.1 have been seen here. The 3.1 effective confinement, and B stress versus strain unconfined. We can see here another picture which shows the typical behavior of column confined by closely spaced but spoil but not failure. We have been seeing the spoil but not failure, and light and confined and failure, tie and drilling measure earthquake. We have been seeing here the spoiling but not failure. Column is closely spaced spiral empirical by USA. This is this column. And another we have been seeing failure lightly confined tight column. Not this USA. This is the failure of column, but this is not our failure. It is the spiraling of column. We can see here shear versus flexural failure. Shear failure occur due to tensile stress in concrete diagonal direction member axis, and the failure varied side and is not associated large deformation from plastic hinge. We can see here the brittle shear failure beam. This is the beam, the shear failure, and this is the column is also shear failure. Therefore, the preferable mode of failure should be flexural failure, and the design shear failure capacity should be design greater than 1.4 MUL plus MU2 and divided by L plus MU vertical. Okay. We have been seen the here shear versus flexural shown here. The diagram due to gravity load or vertical load we have been seen. The total load will be W L square by 12. Total load is UDL load, and so the In this diagram we can say that the total load will be divided in two portions. One is the support one, which is WL by 2, and another is WL by 2. At Y we can see WL by 2. And at the diagram, due to earthquake, which is lateral load, or it could be uh, uh, wind, so it is the lateral load or lateral load. We can see here vertical load is downward V1, and P2 is upward, and moment is rotating, moment is clockwise, is always clockwise, because the and B1 and the and M1 and B2 will be opposite direction, and in this way M1 and B2 shear moment and shear will be at opposite direction, due to resisting the earthquake. So how we'll get this? At first we are taking moment is here, W prime 2 into L, which is taking the minus direction, as we have been seeing the it is taking the positive, and plus M1 plus M2 B2 is it upward direction, that's why we have been using minus sign. If we calculation by is a gravity direction, then we have used the positive sign. And M1 and M2 is a clockwise, is as it is clockwise, that's we are using the positive sign. So in this way B prime B2 prime, this is the B2 prime, and B2 prime will be M1 plus M2 divided by L. So these are the equation we have been seen how we'll get the B2 plus M2 divided by L. Okay, so let's see the design shear due to vertical load. We have been found WL by 2, as we have been seen here, and due to earthquake load we have been seen how we'll get this earthquake load M1 plus M2 divided by L. So the design shear will be vertical plus 1.4 or M1 plus M2. Why we have multiplying 1.4? So in this purpose we have been in this case we have been seeing the stress test diagram. The strain stress we have been seeing the yielding stress is here, and on the other hand we have been seeing the ultimate stress is here. So between yield and ultimate stress, the space will be multiply. It is 1.4 times of the higher strength of yielding. That's why we are multiplying 1.4. Okay. So another topic we have been seeing the weak beam storm column. So this is the picture we have been seeing. This is the column and this is the beam. The column ultimate moment and ultimate moment of column, the ultimate moment of beam, it will be 1.2 times of the total. So you can see the column ultimate moment will be 1.2 times of the beams. Okay, so why? If you question why, then we can see here the weak beam is from column. It is the desirable minimum yielding is column to make the beam comparatively weak, ensure that they fail before the columns. From observer, the failure of the yielding observer earthquake has have lead to form of the weak beam strong column design philosophy, which is strength the made at least equal to the greater strength. Okay, so we've been seeing the BNBC on other codes. A seismic detailing code are a special provision for ensure such mechanism and some the ultimate moment capacities of all of the column stories record at least 20% larger than some of the ultimate moment capacity of the story beam. That's why 1.2. Okay, so we have been seeing the strong column weak beam causing several damage, which is Burj, India. We've been seeing here. Another is already collapsed in Turkey. We have been already seen how we'll get this the flexor versus shear. We have been seen how we'll get this formula. We have been already seeing here, and this is the weak beam strong column, and here is the soft story. So where is the stiffness is less, then we can see that this is the soft story. Okay, we can See here, here is the hollow. This is the soft. The story will be soft. On the other hand, this is not hollow. There, that's why this story will be stiffness will be greater than another one. Okay, how will we can see the desirable it is desirable to minimize the yield in column, make the beam compressive weaker to ensure that failure before column, and observe the failure due to yielding in column. Previously earthquake have lead to formation and for formulation the weak beam strong column, and design philosophy column strength at least the equal of the beam. Okay, I have already read there, that's why I'm not reading again. This is the sorry. The most frequent failure mode of reinforcement concrete building is called soft story mechanism. In many building, architectural consider require of open ground is called soft story for commercial purpose or other use of parking where the ground safety does not have the partially walls and either the masonry of RC between them, and another typical case rise when the ground story is made taller than the adjacent upper story, which is also case the soft story formation drastically change in steepness between adjacent story, but such building has a relative. Okay, we have been seen here the soft story ground story failure in San Francisco, USA, and Algeria. We have been seen here the reinforcement detailing and discontinuity. We have been seen here. Another topic is short column. We have been seen B equal to which is 12 pi by L cube into del. As we know, P equal to Ku. P equal to Ku. Ku means K delta, and K equal to 12 pi by L. So, if the length is small, then shear will be increase. As the length value is low, then shear value will increase. So we can see here the building is sloping here. So this column will be take more shear. This column, this pier will be more shear. Okay, let's see the short column. The column that are partially resisting along their height are called short column or competitive column. Short column are seen in maybe situation in building column where wall masonry RC and partially height of the limit is remaining height fit with the window. Okay, we've been seen here short column effect and shear failure of short column. We've been seeing here shear failure of the short column due to the short. So let's see seismic detailing of material. Concrete prime C is greater than 3 KSI for 3 stories or taller building. For good shear and good bond strength, and still must be less than 60 KSI, preferable 36 still, and the ductility ratio of A is greater than Fi divided by Fi, which is 1.2. We've been seeing 60 grade, the 60 grade bar is failing here. The taking the ductility is less. On the other hand, for 40 grade steel is taking the much ductility or much strength. So in this case, seismic for this seismic design, we will avoid the seismic grade 60 grade rather than we have been use the 40 grade or 50 grade, as the higher grade of steel is lower ductility. Okay, so you can see here measure the detailing of the flexural member, whose member is factor axial loss is um, um, less than apparent C divided by 10. Okay, size we can see here size B divided by 10. B divided by 10 is greater than 1.3 to ensure the lateral stability and improve torsional resistance, and B must be greater than 10 inches to decrease geometrical error and to facilitate rod placement. And D must be LC divided by 4. LC is the clear length of the beam. So you can see here the some failure. Here is the shear failure. Sorry, this will be flexural failure. This is the shear failure. This is the shear failure. This is the also shear and diagonal failure. We don't want to fail in shear. That's why we will using more longitudinal lever at least two. We'll see how many because it will be warning. We want to in this beam we want the beam will be fail in shear flexurally, because it will be warning. It will give the warning before the failure. On the other hand, in the shear failure, sorry, in diagonal failure, this is the flexural failure. Okay, and the flexural failure we don't we want to this. We want the beam will be fail in flexurally, because it will be takes more time to gives our warning. But we don't want this type of failure. This is the shear failure, because it will be failed in suddenly and it will be collapse, and the beam will be collapse on our head. Longitudinal reinforcement and a stop, so we have to provide the top at greater than 2 and bottom also greater than 2. So rho will be 10 root over f times c fy. If you calculate it, if we use f prime c 3 ksi and fy equal to then we can see here f 0.107, which is 0.200 fy. Suppose the brittle failure. So here is some code prescribed. So I'm just reading from here from the side slide at the sir. So you've been here the material. At first we've been seeing the material must be 3 KSI. For weak concrete have lower shear and bond strength, and Fu less than 60 KSI has lower strength, have the longer yield region and greater ductility, and greater Fu divided by F ultimate divided by yielding ratio. So major seismic detailing we have been seeing here, the major seismic detailing of flexure, that means beams. Specifically we have been seeing B divided by T will be greater than 0.3, which ensure the lateral stability and improve torsional resistance, and B will be greater than 10 inches, which will decrease the geometrical error and facilitate to the rod placement. And D will be LC divided by 4. LC is nothing but is a clear distance, and B the possible explanation will be behavior design depth member of significant differ, and the top and bottom rod will be greater than 2, must be construction the construction requirement. So rho will be we have been seen 0.00 how it's 0.002 0.2, so it will be 0.2 at both top and bottom to avoid brittle failure of cracking. So less than 0.02 at top and bottom to causes yielding before the concrete crushing and avoiding the congestion. At first we have been seen here top and bottom we have been use the rho greater than 0.002. If we use the rho less than 0.002 is top and bottom to avoid the steel congestion. The top reinforcement will be 0.05 as top at joint, and top divided by bottom the ratio will be 0.25 as top maximum section, because to ensure the adequate ductility and minimum reinforcement for moment reversal. So we've been seeing here both top and bottom bar, and bar at the external joint must be anchor which is greater than development length plus 10d into d beta of bar from the inner face of the column, which is bend 90-degree bend. To adequate encourage and joint ductility. This is the possible explanation. The left splices allow for greater than 50% of bar, where only where stirrup is provided at the rate of d divided by 4 or 4 inches center by center. The possible explanation is closely spaced stirrup is necessary within length and because the possibility of loss of the concrete cover. So left splices length it will be greater than LD, which is development length, are not allowed within the distance of 2D from joint or near possibly plastic zone. So left splices are not reliable under cyclic loading into the elastic region. Okay, so let's see the web reinforcement. The web reinforcement must consist of the two closed vertical stirrup within 135 degree hook and 10D, which is 10 dt, which is greater than 3 inch extension, to provide lateral support and ensure the strength development of longitudinal bar. So design shear force is maximum of shear force from analysis and shear force due to vertical load joint plus is required the flexural yielding joint. It is desirable that the beam should yield in flexure before the shear failure in shear. The spacing of hooks within 2D beginning at less than 2 inches and at either end of the beam be d by 4, which is 6 dB, or elsewhere will be as less than d by 2. Possible explanation is provide the resistance of the shear and confined concrete, improve the ductility and prevent the buckling of the longitudinal reinforcement bar. So we have been seen here that 4 reinforcement is provided. Here is a 10D, which is greater than 75 mm. This is the hook, and cross section we have been seen here, U shape, and the maximum we have been seen here as maximum BD and rho max is less than maximum BD. So this is the 2D, which is the spacing will be much dense, and after 2D is 2 side, that will be another dimension, and the length the hoops is spacing d divided by 6, and this hoops ends 8 cb. Okay, we've been seen here. So let's see another, which is measure seismic detailing axial member. This is the beam, so we have to this is the flexural member or beam. We have to must be keep in mind. So this criteria will be must be fulfill, otherwise it will be disaster. Now we will see the axial member, which is measure seismic detailing axial, which is column member whose factor axial is greater than FLC by divided by 10. So we can see here B divided by AC will be greater than 4. The possible explanation is to ensure lateral stability and improve torsional resistance. And BC, the dimension will be greater than 10, and to avoid slender columns and column avoiding before the beam. Okay. So we have been we are already the failure mode. We have been completed transverse versus compressive reinforcement completed, shear versus failure completed, weak beam, strong column completed, soft story completed. So these are the we have completed. Now we are going to code prescribed seismic detailing RC column. At first we have been for material we are discussing here the meso seismic detailing for flexural member whose factor stress is less than 10. We have been completed here. Now we are describing this phenomena. Okay. So we've been seeing the left splices are allowed where only 50% of bar only allow stirrup is provided at the rate of B divided by C or 4 inches. The explanation is closely spaced stirrup are necessary with the left length because the possible of loss of concrete cover. So left plus is length greater than development length, the only allow the center in half of the column, and left spices are not reliable under the cyclic load into the inelastic range. Okay, so the row will be 0.01 to 0.06, between 0.01 to 0.06, to ensure the effective and avoid the anchorage of the longitudinal bar. And we can see here a strong beam with column condition within the column will be greater than 1.25 beam moment. To obtain strong column with beam condition to avoid the column failure. Okay, let's that was the longitudinal reinforcement condition. Now we'll see the transverse reinforcement. Transverse reinforcement must be consist of closed spiral of rectangular circular hook within 135 hooks with 10 dt transverse which is greater than 10 inches extension. Explanation is to provide lateral support and ensure the strength development of longitudinal bar. Parallel log of the rectangular hooks must be spaced less than 12 inches center by center. Okay, so provide lateral support and ensure the strength development of longitudinal bar. The spacing of four hooks within L naught, which is greater than LC, and AC divided by 18 inches square at each end of the column must be BC divided by 4 or 4 inch, or elsewhere the spacing will be BC divided by 2. The explanation is provide resistance shear and confined concrete to improve ductility and prevent buckling of the longitudinal compressing bar. So design shear force and maximum of shear force. From the analysis, the shear force required to flexural and yielding joint. This is desirable that the column should yield in flexure before failure in shear. Special confined of reinforcement, the spacing will be less than B divided by 4 and 4 inches square. What should extend at 12 inch into any other footing. And the explanation is the possible explanation to provide the resistance to the very high axial load and flexural demand at the base. Okay, let's see another point, which is the special confinement reinforcement. The spacing will be same, B divided by 4 or 4 inches square, which is greater. It should be provide overall the entire height of the column and supporting discontinue stiff member, and extend LD. LD means development length into the member. And the explanation is this discount is stiff member, which is shear wall and masonry wall, bracing and mezzanine floor may be developed significant floor and the considerable inelastic response. Okay, let's see another point for transverse reinforcement. For special confinement area where circular spiral, as we know, 0.11 S into D FMC divided by Fy as minus FMC into 1. And this condition must be fulfilled for when the column will be circular. On the other hand, we can see if the column is rectangular, then the hooks will be 0.3 ST FMCT. This criteria must be fulfilled. Why? The explanation is given here to ensure load carrying capacity up to concrete spoiling, and taking into consider the greater effectiveness of circular spiral compared to the rectangular hooks, and it will also ensure the toughness and ductility of the column. So this is the must be we have to keep in mind. So let's see and the seismic detailing of column. We can see here the AC is greater than 300 and H prime C also less than 300. Here is a cross tie, which is BC greater than 300. This is the 10D, 10D, which is greater than 75 millimeter. Okay, we can see here this is the column with the joint reinforcement as per 81. You can see this is the tie, and the length will be h divided by 4, and this length will be h divided by 4. And in this region we can use the tie or spiral with less density. But on the other hand, when we will be use the splices, then we have been used the splices will be dense. Okay, as we have been seen spiral confinement reinforcement as per 7.1, and the in the joint, up to joint of the beam column we have been used the dense of the, what I will say, spiral tie or spiral. Okay, so we have been completed here. Okay, let's see here the okay, we have been completing here. So let's see measure seismic detailing of joint frame. So let's see what is the criteria of joint frame. Okay, I'm taking here from here the measure seismic detailing for joint frame. The transverse, at first I'm delivering about the transverse reinforcement. The spatial confinement of reinforcement, the spacing will be less than b divided by 4 or 4 inch should extend it through the joint. The explanation: to provide the resistance of the shear force transmitted by frame member and improve the bond between steel and concrete within the joint. And another spacing will be b divided by 2 or 6 inches throughout the joint with beams of width which is b divided by 0.75 bc. The explanation is the confinement is provided by the beam for framing into the vertical factor. Okay, let's see here the seismic detailing of the flexural member. So flexure, that means beam, moderate seismic zone. So this is the very important. So we've been seeing at first the longitudinal reinforcement. Longitudinal means this is the beam, and the longitudinal in along the length of the beam. This is called longitudinal. So as bottom, so if we consider this beam, so bottom, this means this, the bottom reinforcement will be greater than 0.33%, one third of the top, one third of top. Okay, if we use the 3 river in the top, then we must be use greater than one bar, which is one third of top. That means we have to use two bar at joint. In the same way, we've been seeing the as bottom divided by top ratio between bottom divided by top. It will be greater than 0.25 as top, which is maximum at any section. Why? Because to ensure the adequate ductility and minimum reinforcement for moment reversal. So web reinforcement we have been seeing here. Design shear force with the maximum of shear for analysis. The shear force due to vertical joint plus as required for flexural yielding joint considerable minimum moment instead of probable moment. It is desirable that the beam should be joined at flexure before the failure of the shear. So you can see here the spacing of hoops within 2D beginning at 2 inches, and either end of the beam must be d divided by 4 or 8d or 20 dB dia of main bar, and 24 SD is stirrup dia, and or 12 inch or which is greater, and elsewhere we have been which is the lower, and elsewhere we will use d divided by 2, because the provide the resistance of the shear and confined concrete improve the ductility and prevent buckling of the longitudinal compression bar. So another is seismic detailing for axial, that is called column. Is the modern seismic zone. We have been used the beam column, strong beam with column concept, which is column moment will be greater than 1.2 type of the beam moment. And the web reinforcement, the design of shear force is maximum shear force from analysis, and shear force is required for the flexural yielding of the joint, and desirable that the column should yield in flexure before failure in shear. Okay, so let's see the spacing of the hoops within L naught, which is greater than DC or AC divided by 4 or 18 inches at the each of the column, and must be 8 dB, which is diabar, and 24 SD stirrup diab stirrup, and one third BC or one third AC, or 12 inches, which is less. We have been used this, or elsewhere we have been used stirrup 2S naught. Why? Because the provide resistance of the shear and confine the concrete improvement ductility and prevent buckling of longitudinal reinforcement compression bar. Okay, these are the ending here. So let's see another. This is the joint measure seismic detailing of the detailing for joint frame. It is completed, and seismic detailing for flexible member in moderate zone. It is completed, and seismic detailing for axial member in moderate zone. It is also completed. Now we'll see the ductility design of shear wall. Okay, let's see here. This is the shear wall. The RC shear wall in perform much better if design is be ductile, and overall geometric properties of wall type of amount reinforcement and connection remaining element in the building helping improve the ductility of wall. Okay, so we've been seeing here. This is the boundary element. This is the most important. So boundary element with increase the thickness. This is the thickness we have been used, and in this year without increasing thickness. Most of the cases we have been using this type of shear wall in our practical field. Okay, so let's see here the reinforcement bar in shear wall. We can see here the reinforcing bar to provide shear wall regularly spaced vertical and horizontal, which is given in a figure, and the minimum area of reinforcement bar to be provide 0.0025 of the cross sectional area. Okay, boundary element. So we've been seen here the under the large overturning effect of the horizontal earthquake forces, and the shear wall experience highly compressive and tensile stresses to ensure that wall behave the ductile way. Okay, so column beam, coupling beam, we have been seeing here the coupling beam is given here, and we have been seeing the seismic detailing also given here. Okay, so let's see, we have been seeing here the building plan. In this case is the building plan is given here, and the moment versus curvature of column is 6 stories, which is C1. This is the C1, this is C2, and this is the C3. C1, C2, C3. So we have been seen here. This is the C3, and this is the C1, and this is the C2. Okay, C1 is corner column, C2 is side column, and C3 is middle column. Okay, we have been seen here the end curvature C3 for L and to 6 stories. A is no, and B is moderate, and C is major detailing. Okay, we have been seen here. A, B, C, there is no. This is the moderate, and this is the major detailing. So let's see another topic. This is the most important, which is seismic design and detailing of RC frame, or we can see the earthquake resistance design of beam column. Okay, so let's see some example. So we've been seen here the design moment to which a keep fit is given here. We've been seen this is the given, and the combination also given here, and the following section are obtained used in material properties is given for KSI and 40 KSI, and we have been seen here number 3 a bar of tie at the rate of 12 inches center by center, and here is that 10 number of 4 bar is used here. The column section is with the reinforcement. We have been seeing beam and slab without reinforcement, and this is the section we have been seen the beam, which is the section A, B, C, D, E, and through. We have been seeing the A portion, this portion. So this portion we have been seeing the two reinforcement in bottom and three reinforcement tie, and the middle is the extra 7 bar. So two reinforcement is continuously. We have been seeing here two number 5 is thoroughly used. We have been in beam. For section B, we've been seeing here the all the reinforcement is given, and we have been used extra wall 5 number of bar, and section is given here C. Okay, section C we have been seeing this type. This is the section C. Okay, so in section D is here, section E is here, and section in this way we've been used two type and throw. Okay, so let's continue. As per our design, we have been used concrete, which is design condition. We have been used 3 KSI, so this is okay. Specification is given is apparently greater than 3, but we have been used 3, though it is okay. Still, we have been used less than 60 KSI, but we have been used design category, we have been used 40, so this is okay. So flexural or beam member, the member where factor load is apparently by 2 divided by 10. The specification D by B, which is 0.3, and design category which is found B is 12. So we've been seen here B is 12, and D is 13.5. So B is given is 12, but D is 13 point. This is the 13.5. So it is given 0.89, which is greater than 0.3. So it is okay. So B, the specification is given B greater than 10. We've been used B is 12, as we've been seeing here. Unfortunately, it is not given here. So it is given here. So we've been used B is 12 and D is 13. So sorry. So that's why we have been used. So it is also okay. So size we have been seen LC divided by 4. LC which D is given 12 plus 4 minus 2.4. So this is 12 and this is the 4, and minus this will be deducted in covering, and from 13.5, and LC divided by 4. LC is 12.5 minus 4 into 12. This is the length we have been seen here. This is the total length. Okay, or we have been found here. Okay, and divided by 4, and from 36, which is given, so it is also okay. So number of top we have been used, we can see the specification is given greater than 2. Number of top bar is 2. We have been seen all the top bar is 2. All the top bar is, we have been used all the top bar is 2, and bottom bar also 2. So these are also okay. So row value will be this. So we have been used top row 0.1 root over F times Fy, and row will be top divided by BD. Top pi we have been used number 5 bar. So pi divided by pi into 5 divided by 8 square into 2, because we have been used to 2 number of pi, and found 0.0038. On the other hand, could prescribe this value, and we have been putting this value and found 0.0048. So this is not okay. So this is not okay. You have to redesign and modify the check, modify the what I will say, modify the design, and we have to use the more top as top for getting the higher value. Okay, as bottom at joint 0.5 as top and as bottom and top 0.25 as top or max. So we've been seen as bottom is greater than 0.5 as top, as we have been seen as top all the greater than 0.5 as top, and as bottom we have been use 2 into 6y, so 2 into 0.61 is the 60. We have been use the number 5 bar, and we have been bound 0.61 as could prescribed. We have been seen 5 into 2 into 0.31, which is also 0.31 is greater than this below. This is the 0.31 and this is the 0.35 50%. And another section we have been seen as top and bottom 2 into 0.31. We have been used the bottom and top throat at the 5 bar and found 0.61, and 0.25 as top and max we have been found 0.25 in 1.22. So and found 0.31, which is greater than okay. So this is also okay. And this we have been seeing all the parameter we have to check. How we'll check? We've been 0.89 at first. We have been found where 0.89. This is the 0.89. So this is the 0.89, 12, 0.95 bottom, 0.33, 0.75, 0.3, and these are the all the okay. Maximum row we've been found 0.35 and as top 0.621 square. Okay, so we've been seeing the all the specification both top and bottom bar and extend and join bar, so need to be specified, and all the other is need to be specified. We've been seeing the this calculation spacing of holes within 2D, which is 27, and the beginning to 2 inches square either beam, and found B is D divided by 4 and 8 dB, which is found 8 at 3.3 inches square and 5 inches square is where we have been at 6.7. But we have been found 6 inches square 6.75 and center by center, which is D by 2 through the beam 6.75. But we have been found is here the less below 5 inches or 3.35. That's why this is not okay. Please open the door. Okay, so we have been seen here the column. Here is the axial member, which is the column. The specification given is BC divided by 4, which is 4, and design condition have been found 0.92, and B is greater than 0.12, which is 2. This is also okay. So all the parameter we have been seen here. The ratio is we have been used between 0.1 to 0.6, but we have been used we have been found 0.029. So this is also okay. And parallel legs in rectangular hoops must be spread, which is 12 inches square. This is also okay. So hoops we've been seeing here. Hoops is spacing within LD divided by DC AC divided by 4 and 18 inches, and we have been found here 10 and 18 and 18 inches at all the calculation, and each of the member, each of the column we have been found 3 inches square, but we have been used 12 inches square throughout the column. So this is not okay, so we have to modify this and recheck. And we are using this we can see spacing. We have been seeing here the spacing D divided 2, which is 6.75. We have 6.75, and the spacing within 2D, which is 2.75 to 27. So we have been found is 27, and beginning at 2 inches square either this below, which is 3.38 inches square and 5 inches square, and elsewhere we have been used 6.75, and this is not okay. And joint frame beam column joint we have been found here. The specification specify confined reinforcement which is extended to the through the joint it not specify. And the transverse we have been seen here the 6 inches, and 6 inches through the joint is beam we have been found 0.75. On the other hand, in the from this we have been used b is 12 and bc equal to 12, but no stirrup is specified. Okay, so since b divided by 0.75 bc and st is 6 inches square through the joint, so we are all using this now. Design and detailing modification, so we have to modification. At first, correct as for beam we have been used. If all beam are number 4 bar are used, change to 6 bar. So let's see. This is the our number 2, number 5 bar we have been used through. So this bar we have been changing through. We are using 6 bar instead of 5 bar. So let's see how we will calculate. So the row below will be changed as top divided by BD. So we have been use number 6 bar, and found this calculation by display by 4 and 2. 2 is as we have been used the 2 bar, and we have been found 0.02. So this is okay, and previously that was not okay. We've been seen here the lots of the shear capacity have been found. FD is a vertical from analysis by ETFs or hand calculation, and FD we've been used 33 or 29 or 77 or 78 from load combination. And this is the load factor we have been found, which is 1.2. 5 is 9.6 is 14.4. For beam B1 B60, B60 means let's see here. B10 12 60, this beam. So let's see beam 60, as we have been used this top and found 1.9, and moment will be for section A and found 61, and A we have been found 1.31. Moment BB section we have been found 5.6, and B design 1.4 E1 M1 plus M2 divided by L, and vertical have been used 1.5 as we were known 1.4 plus 1.6 divided by 2, and that's why 1.5. And we have been found 28, which is greater than 14.4. So this is this is okay. There is no doubt at all. So it will not fail in earthquake. So we have been using this criteria 1.4 plus 1.6 1.41 inches square. This is the remain 0.88 inches square, as we have been used number 6 bar in 2. Okay. Let's see another beam, which is beam for B20, which is B20 70 okay. So B20, okay, we have to see which is B20. 14.4. Where is 14.4? Okay, we have been found here 14.4, but we have been calculating, we have been found 28. So this is the 28.4 is greater than 28, which is greater than 14.4. Okay, so you can see this is the okay. So another beam is B20. All the data is given here. This is the beam 20 data we have been seen here. So in this way we have found 61 and 52 from previous calculation. Yes, 61 and 56. Okay, so design we have been found 33.85, which is greater than 9.8. Here is a 9.8. So this will be okay. Now we'll calculate the shear capacity and found 17.75, and shear we have been found 20, 10, 30, 3.35. So this is the calculated 33.85. So so shear will be designed 33.85 because of we will taking the maximum value. Okay, and the maximum shear spacing we have been using this formula and found 5.38 inches, which is less than 6.75. So not okay, as we have been seeing 6.75. I will get 6.75. Okay, we have to seeing 6.75 spacing. Six 6.75. Okay, let it down. It will be 5.38, which is less than 6.75. Oh, okay, 6.75 is d divided by 2, which is, we know this is the 30, and 30 by 5, and 30.5 we've been seen at firstly we've been seen here 13.5. This will be 13.5 and divided by 2, which will be 6.75. So these are the not okay. We have to redesign. So instead of 6.75 is not adequate, but special transverse reinforcement are 3 inches close to the joint. So we have provided two number 3 bar type at the rate of 5 inches square. We have been found 3.738, but we are using 5 inches square center by center. Okay, these are the steel facing we have been seeing 3.35, but we are using 5 inches square, not 5.3 but 5 inches square. Okay, now we will checking the shear capacity of the column. For column C2 we have been seeing there is no value is given here. We have been found 130.8 in the previous data. 130.8 where okay, okay, 130.8, it will be multiplied 1.4 times, and on 13.2, 130.8, column 2. So column 2 is this column 2. Where is column 2? On 30.8. Okay, I'll see where we have been found 130. This is the ground floor. Okay, 130.8, 130.8, 130.8. We'll get this 130. It may be the axial load we have been found in calculating. Okay, let's see how we get. And okay, this is the 130 is calculating dead load, live load, and floor finishing and partition wall and in this way I found 138, and it will multiply by 1.4, and it will be ultimately 183.2, and found 0.56, and rho is found 0.58, which is 6, and we are using this and found a is equal to 0.44, and rho have been used 0.025, and which is 2.5%. Now we will go to the this chart. So let's see here. Check the shear capacity of column. We've been seeing here the column size is here 130, and this is the graph we've been found. This is the graph. So from this graph we have found row 5.6. I will get this is the 5.6. This is the value of K, and this is the value of K, which is 5.6. This is 8, 6. This is the 5.6. So this value is taking here, and 0.18. Why will taking 0.8? Because the row is getting 0.02, which is the 0.5, 0.3. This is the 0.3, 0.2. So this will be 0.5. So the value will be 0.15, almost is 0.18. Okay, in this way we have been found there, and we are taking putting all value and found moment, which is 75.82, and B design we have been found 235 net key. Okay, and this is the column C2. For column C6 at ground, so this is the column C6, and found this value, and putting all this value and found 0.60, and in the same way is row value is found. After the getting all this value and putting this graph, column interaction graph, and found 0.17, and M value will be putting all this value, M value point as 17.6 kg per feet, and design B design will be 22.28 kg. Now the shear capacity will be 13.53, and shear design shear will be 23.59, and shear will be seen the maximum is found 23. The show B design will be 23. So maximum will be putting all this equation and found 5.18 inches square, but we have been used 12 inches square. So this is not okay. So we are using 5 inches square. So stirrup spacing provide 8 inches square through the column is not adequate. The provided number 3 bar provide 5 inches square, but we have been found 5.88, but we in practically we have been used 5 inches square. Moreover, special transverse reinforcement are placed 3 inches square close to the joint. Okay. So now we'll checking the moment capacity of joint, which is weak beam a strong column. For ground we have been since C6, and P we have been known this value is found dead load, live load, and flow finishing partition on multiplying with 8. And in the same way we have been found 6, and rho will be gamma is 0.6, and rho will be 0.06. So from graph MC we have been found 17.60 from previous calculation. 17 point here 17.60. So we are taking here the value is taken comes from here, and from first column we are using 3/4. Second floor we have been used 2/4, and third floor we have been 1/4. If we calculate taking memorize from upper, then first will be 1/4, this will be 2/4, this will be 3/4, this will be 20% less. Okay, so after putting this value and found the value of this value is 0.45 and gamma is 0.6, then will be found the row of value from this graph. And putting this value, all the values putting here, and found moment is 80.03 keep fit. And column will be column 1 plus column 2. So column 1 17.61 in calculation in previously we have been found 71.60. Now another column we have been found 80, and we are total beam uh, and the total column will be beam 99.75 K. So column we have been found 151.6. This is the 151.6, and 1.2 is beam which is 99, and found 119. This is the okay. So strong column with beam is condition is okay. So this is the final graph we have been seen here. After calculating all the after all the calculation is done, so so we have been the following chosen column, which is 10 number 6 bar 130 hooks and 4 leg is size 3 inches square this, and this is the extra we have been used 7 inch bar and 6 bar also, and 3 inch 4 extended. And this is the final diagram we have been seen here. We are changing this reinforcement, and at the beginning that was 2 into 5 number 5 bar, but we are now using 2 number 6 bar. And this is the spacing, this is the 18 inch spacing, and this is the LC divided by 4, which is 27. This is the LD divided by 27, and this is the another. So SP is given. SP means this is the SP, this is the SP. So SP means 2 leg 3 number stirrup 3 inch square center by 3 inch square length 27, and this is the SP. So we are using the here. And CSP, this is the CSP column. CSP, the 4 leg number 3 bar stirrup and 3 inch square is throughout. Okay, so we have been another here the anchor at the joint LC development plus 10D. So LD development bar we have been using this formula 0.00 as FY divided by FMC, and found the development is 24.53, and the launch will be 24.53, which is development length, and 10 into L divided by 4, which is 33.29, which is used 34 inches square. So in where the development and length is needed, then we have been used 34 inches square. Okay, so this is we have been seeing here. The SP is given, and 2D 2 into D into 27. So we have been found 27. 2 by 6 we have been used. And the top reinforced one. The extra we have been used 1/7. Here is the LC divided by 4, which is 27. We have been here. This is the 3 stirrup at the rate of 6.75 center by center. We will calculating here, and the SP will be already seen here 3 inches square center by center. And this is the 18 and LCH is 34, because we have been calculating here LCH. This is the LCH 34. This is the LCH. Okay, LCH as development length plus 10 DO. So development length formula is here 24, and LDO in 34. So this is that LT4. Okay, we've been see here the all the data is given here. Okay, let's see another example. With a given RC beam column section is shown figure. Calculate the distributed W. So we have to calculate W. So keep fit and beam AU, and here is the AU. one story and ZIUL, so ZIUL shown in figure. If the column ZA, so this column ZA is satisfied weak beam is strong column condition, checks is ZAL. This is the AL second story. Two stories is JAL's story in weak beam weak beam strong column condition. The distribution WU keep it calculated. Okay, so we've been seen here all the data is given here. Then the depth is 30 into 4. This is the 12 and this is the 16. This is the column section. This is the beam section. So six number bar we have been used, and the stirrup is 3 stirrup and 4 inches center by center. This is also 3 stirrup and 4 inches center by center. But column section in the main reinforcement number 8 and number bar we have used. So beam AU. So this is the AU first beam. B is given 12 and D is given, and AS we have been found. So AI will be 2.16. So moment we have been found 73.82. To satisfy strong weak beam strong column condition, the column greater than beam. So 1.2 into beam we have been found 73.82 in beam, and which is 88.85. Now for 14 by 40 column we have been putting all this value 88 into 12 and found 0.143, and the steel column reinforcement ratio will be 0.03. So as we know this 0.014, this is the 0.014 from this diagram. If we know the 0.143, so 0.143 will be here, and the row is found 0.03, so the row will be 0.03. That means this is the row graph of 3. If I will change the color, then we have been seeing this is the 3 graph. So if this graph is intersect here, then we will go here in this direction. Okay, so in this way we have been seen here, we have been found 0.92 from the graph, and putting this value and found P values 3.379 kip. Now we are using W for we know the W, and the support will be W divided by 2, and this will be W divided by 2, and the W will be 47.4 kip feet. You can see here the top story AL satisfy OKL for 2 stories the building. That means 2 stories AL column and 1 story Z is satisfied, because 2 stories is joint L one column and 1 beam, which is 1 story building ZA is 1 column 1 beam. So this is the 1 story building, which is 1 column 1 beam, and this is the 1 column. So joint A you can see has a similar beam and 2 column. So joint A similar beam and 2 columns. So this is the 2 column, and including AL, which is satisfy its own, and therefore weak beam strong column condition satisfy OBS. So you can see 2 stories building at joint A. So this is the joint A, and the 2 columns, so column 1 column 2 plus 1 beam. So this is a 1 beam. That's why it is satisfied, because 2 column in this where 2 column is more strong. So I think this lecture is ended. we have been seeing here. And in another day will showing the earthquake resistance design of flat slab and earthquake resistance design of steel structure. Okay, so if you have any question, then let me know. As this as we have been seeing, this is very complicated, what I would say, the complicated calculation of earthquake resistance design. If you have any question, then let me know. So if I will say again, the failure mode of RC structure, which is the transverse and compressive reinforcement shear and flexural shear, weak beam, strong elements of Storey. This is the theory. And the code prescribes seismic detailing. We have been seeing seismic detailing materials, seismic detailing flexural members, seismic detailing axial, and seismic detailing frame joint, flexural for moderate risk zone, seismic detailing from axial member, and moderate risk zone, and ductility design of shear. And then we have been shown the earthquake resistance or seismic design and detailing of RC frame. These are the main important which I am trying to showing you how will I calculate this individually. If you don't know, if you know how will, then let me comment. I will try to solve again and showing you. You just comment here, then I will try to do again this example and this math and this lecture. Thank you everyone.